continue the session with Professor Zoltan Dienes, who's here from the University of Sussex. Zoltan has his own lab where he works on many different things, decision making, and I think relational reasoning also, metacognition.
Metacognition, yeah.
But in addition to that, he's written some very helpful textbooks on applying Bayesian statistics to your data testing and getting some more value out of your null effects. And I also recently learned that your grandfather and great-grandfather were both mathematicians.
Yes.
So there's a long tradition in his family of making math better for people, I guess. So today we're going to hear from Zoltan about the inner workings of registered reports.
Thank you. So let me first define some terms. Probably a lot of you know, but it's good to be clear. So pre-registration is when you submit your paper to any journal, and as Lisa was saying, you just answer a set of questions about what were your hypotheses, how you're going to test them, what are your tests, and you can put that on OSF or some online permanent place, and then you submit your paper as normal to a normal journal, but you have a timestamp record of your plans beforehand. So that's pre-registration. And that sort of varies quite a bit in the effectiveness to which you have pre-specified what you're going to do and what you're interested in. So registered reports is a more formal format. And the driving energy behind it has been Chris Chambers, who wanted to make sure that everything was nailed so that this could become a gold standard and not criticised for something that became a bit sloppy and got things wrong. So in the registered reports format, it tries to be extremely strict about the whole process all the way through from beginning to end. So in registered reports, what you do is you submit your paper before you've collected the data, so it has an introduction section, method section, and your planned analyses, and they're meant to be planned in sufficient detail that there's no wiggle room afterwards, that you've tied your hands in terms of certain analyses that will test the key hypotheses that you're interested in. That then becomes, well, it goes back and forth. The most rejections occur at editorial sort of desk reject level, often after some back and forth with the editors. After that stage, 90%, as long as it gets past the editors, 90% of registered reports are accepted, at least at Cortex. So it has a high initial acceptance rate. The paper then goes back and forth between you and the reviewers, and once the reviewers are happy that the paper's in good form, that's called a stage 1 acceptance. So that happens before the data are collected, and then you collect the data, and as long as you followed the procedure you said you're going to do, and at least you've done the analyses that you've said you're going to do, you can do other analyses, but as long as you've done the analyses you said you're going to do, and then when you discuss it, you've made reasonable conclusions, then that's a stage 2 acceptance, and that's your paper accepted. So that's the registered reports procedure. Started in 2013 with Cortex, and every time I mention registered reports, I have to look up how many journals are doing. It's now 165 journals, so probably in all sorts of disciplines, but largely psychology. So probably whatever area you're in, and there's going to be a journal that would publish a registered report in that area. In fact, there will be, because, for example, Royal Society Open Science does open reports, and that's a journal. So that's by way of just telling you, make sure you all know what registered reports are. And one thing that's going to be a benefit for you if you're a young career researcher, maybe a PhD student, is once you've got the stage 1 acceptance, remember that's before you've collected the data. So if you think you've got a really good idea, you're going to test an interesting theory and you've got a good way of testing it, you can get acceptance before you've collected your data. As it stands at the moment with Cortex, once a paper has stage 1 acceptance, there's been 100% acceptance at the stage 2 level. Of course, it's not guaranteed, because if you change the procedure or do something else other than what you said you do, it could in principle be rejected. But that hasn't happened yet. There's been 150 something registered reports that have gone through to completion. So if you'd like to get in terms of what's the advantage to you, you can get a publication in principle accepted before you've collected the data. And while that'll take a bit of time, well, it's 9 weeks for Cortex in terms of editorial and reviewing time to get to the stage 1 IPA acceptance level. Then you've got a paper in the bag. You have to run the subjects, but it doesn't matter how the results turn out. It doesn't matter if Nature doesn't really care much for your theories. None of that matters. You'll have your paper, and that's going to look better on your CV to have that acceptance in a good journal. Then you say, I've got a paper submitted somewhere, and then you spend the next 2 years chasing different journals, trying to get this thing published. But there was some little problem in it that you now realise reviewers in the area really don't like, but it's too late to change that. But with the registered report, you would have changed that at the stage 1 level before you finalised the design and started collecting your data. So I hope that's an overview of basically what this is all about and why you might be interested in it. What I want to talk about is what problems does it solve from the point of view of science. And therefore, given an analysis of how it solves those problems, what you have to do in your stage 1 submission, and especially, because then that determines everything else, in order to make sure those problems are solved. Because we're pretty tough on getting it right, everything right, in terms of the logic of how registered reports work. So to understand what you're doing with registered reports, just let's have a little look at what happens in science, at least at a certain grain of analyses. So for there to be a science, I think there needs to be substantial theories. If you're just running around looking at things and saying, I can see something there, and isn't this interesting over here, that's sort of natural history. What we want as a science is a theory in the sense that a number of things follow from it, that it can be tested in a number of different ways, therefore. So that's what I take to be a substantial theory. It's an explanation of something, and it could be mechanistic, and in my view, many good theories would be, but it doesn't have to be strictly mechanistic. It has to be an explanation from which other things follow. So an example of a theory could be, take dissonance theory. Dissonance theory is sort of just a framework for thinking about things. Something that's a bit more of a substantial theory is the claim that extrinsic motivation destroys intrinsic motivation. Okay. A particular prediction or phenomenon that might follow from that is if you say to your kids, eat your greens and then you can have your dessert, that will destroy or at least reduce the intrinsic attractiveness of the greens. So the claim would be this isn't a great way of getting your children to eat your greens, because you might be stopping the very thing that you want to encourage, which is to getting them to like and on their own intrinsic motivation eat greens. So that's what I'll call the phenomenon something which you could say were the findings of your study. So my findings of the study, for example, you could say is telling children that if they eat their greens, they can have the dessert, reduces the attractiveness of their greens. That's sort of finding, right? This is sort of a little bit high-level summary of the results of your study. So that's a phenomenon. So from any given substantial theory, there will follow several phenomena, just results. If this goes up, that goes down, that sort of thing. substantial theory could be mindfulness, meditation, specifically increases metacognitive capacity when it comes to sensory perception. Okay. So then the phenomenon could be, well, when we test people with visual perception, their ability to be aware of their accuracy, to distinguish between accurate and inaccurate, improves, but their ability to make sensory discriminations remains unchanged. Okay? That's a phenomenon. So in order to test a theory, we need to make some assumptions. So we would need to assume, for example, if we test a theory about mindfulness meditation, that the mindfulness intervention actually involved people doing the mindfulness practice. There's always these assumptions that we need to make in order to predict a certain phenomenon and then test it. Then we collect some data, and the data are hopefully evidential in terms of confirming or disconfirming the phenomenon. And then when the phenomenon is confirmed or disconfirmed, if our assumptions are safe, the theory takes some credit or blame in that process. So now this can go wrong at several levels, but one thing I want you to notice about this is what I'm talking about here is a relationship between theories of various sort and at various levels, various claims, and data, evidential relationships. The researcher themselves doesn't really come into this. It's just a matter of relationships between claims and data. It's nothing to do with the researcher per se. Nonetheless, the researcher can play a role in this, in either the process working well or not well. Specifically, and this is what we're going to address with register reports, in terms of when data are seen. So when data are seen, and then this process is constructed afterwards, one problem is p-hacking. So, you can decide how do you get rid of your outliers, which specific analysis do you do, what other factors do you put in the analysis, and so on. That changes the p-value or the Bayes factor, so you can have b-hacking. And what p-hacking does is it renders the data somewhat irrelevant, so the data no longer bear an evidential relationship to the phenomenon. Right? So that aspect of the scientific process becomes degraded. So that's what p-hacking does. And p-hacking is something that happens when you have the data in front of you and you decide on your particular analysis in the light of the data and the theoretical ideas you might be willing to test. But it also degrades at another stage of the process. I don't know if you've had the experience of reading a paper and they describe some theory, and then they say, and we predict this. And they give some interaction or some test. Gelman, in his Garden of Forking Paths paper, goes through examples of this, where he says, well, the authors made these predictions, but wouldn't a simpler test of their theory be this effect? So you can see that the relationship between the theory and the predictions made is no longer sort of simple and straightforward. It seems just a little bit tortuous, but actually sometimes researchers are quite clever about this, and you can be misled and think, okay, that seems to follow somehow. But a lot of the time you read the predictions and you say to yourself, yeah, you knew what results you got when you wrote down these predictions. And the problem with that is that the substantial theory is connected to phenomena with complex assumptions that are unsafe. They're not tested and they're not simple. So they might predict phenomena that aren't really predicted if you thought about it more carefully, or even end up predicting the opposite of what you think really should be predicted more simply. And the other thing that can happen is why bother with the substantial theory at all? You just say, I'm just interested in the phenomena. You just get rid of the theory. Because as long as, see, that's an easy way of getting a publication, especially if the phenomenon sounds sexy. So you just put up your headlines. And this has encouraged a sort of mentality, which I think, of course, we need to establish phenomena. And people were talking about in the history of science yesterday how it's important to establish various phenomena. But I think the balance has gone rather wrong. So now you can have, say, Andrew Gelman, a statistician at Columbia, just read out titles from Psych Science and fall around laughing and encourage you to do the same, because all you have is statements of funny results. That's all the paper consists of. So there's not a theory in sight, really. It's just, here's an interesting phenomenon. Someone said, I wonder what would happen if we changed this. Okay. Here's an interesting phenomenon. So then you end up with something that maybe is a little bit like natural history, but isn't quite science. So writing papers in the light of data is not guaranteed to, but because we're human beings, there's certain temptations to p-hack or b-hack the predicted results, so the data are no longer evidential regarding phenomenon. It invites you to introduce complex assumptions to make the theory fit the phenomena if you have a pet theory involved, so the data are no longer evidential regarding theory. And it can invite you also to give up theory and chasing phenomena and just sort of mindless research, at least from some views of science, say from Lakatos, it wouldn't really actually quite be science. So that's sort of my view of how science works and the places where it can go wrong. So it sort of follows from that. A paper should be accepted if it participates in some aspect of that scientific process, like setting up a substantial theory. A paper doesn't have to do all of those things at once. It can set up substantial theory with some computational modeling or just generating it, talking about a theory. It could consider how you get safe assumptions to make predictions, or how to severely test. It could be methodology and so on. So a paper doesn't have to have all of those components in it to be contributing to the enterprise of science, but it just has to contribute to one of those components. Now, there is a special case of paper in which tries to follow that whole process all the way through to beginning to end. So this is where registered reports comes in. So some people criticize registered reports and say, but this can't be the only mode of submission, but no one ever thought it would be the only mode of submission. It's the particular place for it is when a paper is putting all those components together. I mean, at the moment, we only have 150 registered reports accepted, and I don't know how many millions of papers are accepted. So the danger of it becoming the only mode of acceptance is pretty far in the future. So for your stage one to be accepted, what you'd want is a substantial theory being tested. I'd probably like to say an interesting theory, because, why do we do science? Because we want to find out interesting generalities about some domain, interesting explanations. But my colleague's idea of an interesting theory isn't often mine. So I say a substantial theory. The assumptions connecting the theory to predictions need to be shown to be safe, at least key assumptions. You can't do all of them. And your analytic flexibility needs to be tied down as thoroughly as possible, while at the same time typically ensuring sensitive results. So let's go through those processes. Substantial theory being tested. Cortex phrases and a lot of registered reports have basically taken over Cortex's way of putting things. Submissions will be evaluated with respect to the importance of the research question. Incidentally, I wanted to say before, I never mentioned harking. To me, harking isn't a problem in itself. Harking is something a researcher does, but whether you hypothesize before or afterwards isn't in itself an evil. In other words, metaphysically what we want, in my view, is simply that. And harking per se has nothing to do with that. It's just we have a temptation. The reason why harking has a bad name is when you hypothesize after results are known, there's a tendency for these various ways of process to be degraded. But the problem isn't harking per se. So I won't say more about step one, but just to say sometimes we do get papers which don't seem to have theory in it, and then today is something for you to think about. Next one might sound sort of obvious, but it's surprising. In fact, most submissions probably don't tie this one down. The assumptions connecting the theory to the predictions should be safe. The terminology Cortex uses is and it refers to outcome-neutral tests, which sort of means manipulation checks is probably a more usual term for that. It's outcome-neutral because these tests are neutral with respect to the main predictions being tested. So what Cortex says is full descriptions must be provided of any outcome-neutral criteria that must be met for successful testing of the stated hypotheses. In other words, given your predictions and the main test of those predictions, what has to be satisfied for those predictions to be valid tests of the theory? And those assumptions, which I call the safe assumptions there, will often need to be tested. The reason why they need to be tested is if you got results contrary to the theory, then it's not just your theory that could take the blame. You always have the option of saving your theory and blaming something else. So the things that are likely to be blamed are the things we need to make sure are safe. So for example, a substantial theory could be belief in free will induces one to overcome automatic habits and hence behave prosocially. That's a theory that's out there. And one way that's often tested is get people to read a particular Francis Crick passage where he says determinism is true, you know, and it's meant to be this is a great Nobel Prize winner who says there is no more free will. After reading such a passage, will someone behave aggressively? In one way this had been operationalized in the literature was how much hot sauce you give someone who say they don't like hot sauce. So there's a particular prediction, and obviously there's a number of assumptions that are made in order for that. If that prediction was failed, how well would you feel inclined for the substantial theory to take blame for that prediction failing? So one assumption, just for example, is that the intervention reading statements about free will actually changes free will beliefs. Now, if you didn't test that and you got a result opposite to your theory, you could say, well, we didn't change free will enough with our intervention. You don't blame the theory. Now, what you find a lot of people do is they don't put in the manipulation check. Instead, they run it without the manipulation check, and they say, well, if we get the result, then obviously the manipulation worked. That's a common form of reasoning. But the trouble with that is, if you don't get the results that you predicted, then what? Okay. So in registered reports, what we want is you're tied down. You're saying the theory takes the blame. So you need an outcome-neutral test. In this case, for example, that belief in free will actually changes. That's neutral with respect to the test of the prediction. So outcome-neutral tests must be specified. So that's one thing to bear in mind when you submit your registered report. What are the tests you would have to have in place to make sure the credit and blame transmits to the theory as much as you can judge? These things are always open to criticism later. Just bear in mind when you put in your submission that this is my outcome-neutral test. If that test fails when it comes to collecting the data, you're no longer guaranteed publication at stage 2. So in other words, one of the criteria of stage 2 publication is that your outcome-neutral tests were satisfied. So think carefully about what your outcome-neutral tests are going to be, and you might want to pilot things first to make sure that the outcome-neutral test would be passed for the intervention that you have in mind. Of course, you might want to do other sorts of manipulation checks that might be interesting, but distinguish the ones that must be passed from stuff that's just kind of interesting to know. But this other stuff that's kind of interesting to know isn't a deal breaker if it fails. That's something you have to be clear about when you do your stage 1 submission. To me, one of the key things about registered reports is analytic flexibility being tied down. So let's say you're doing standard significance testing, name and Pearson inference, as it puts here. To ensure sensitivity, and you're doing normal p-value type stuff, then you need power. You need sufficient power. So we lay down a power of 90%. Now, you've probably come across a debate about significance. Standard level of significance is 5%, and should we be tougher? Should we leave it as it is? As of last year, Cortex did a little, has started doing a little experiment. I mean, there was that paper that said 0.005 instead of 0.05. We decided not to go all that way, so we've gone to 2% significance. So bear that in mind. So it's 90% power for a 2% significance level for standard significance testing. This isn't true. I haven't checked all the 150 journals. There might only be Cortex that have gone to 2% significance. Others are probably 5%, but that's something worth checking when you submit what is the significance level. So we're asking for 90% power at Cortex, 90% power for 2% significance. I noticed there's one exception to the power requirement. The other places that do registered reports that I've checked do have a power requirement. Royal Society Open Science has made a deliberate decision not to have a power requirement. One of the problems with literature people often talk about is low-powered studies with respect to the effect sizes you'd be interested in, and so Registered Reports Cortex tries to crack down on that. I mean, there is a good reason for cracking down on that as well within the internal logic of registered reports, which, when it comes to manipulation check, that if you need to guarantee that some outcome neutral test is satisfied, sometimes your outcome neutral test might be no difference between something. Well, the only way you can satisfy that test is if you've tested it severely or sensitively and come up with a conclusion of no difference, and for that you would need high power, right? But Royal Society Open Science, at least when it comes to your main prediction, is implicitly saying the main problem is to get an unbiased literature and to get publication not based on results. And even if something's a bit insensitive, it's still worth having it out there. And there's good reasons why it might be insensitive. If it's a clinical population, data really hard to get, we don't want to lose that just because the study's not being run on weird undergraduates where you can just collect 60 every term. So do have a look at the requirements when you submit, because there are some variations out there and you might find some of them suit you better than others. Now, what I want to mention is why is tying down analytic flexibility a good thing? So this is how I think about it. Again, what I think is relevant, there's nothing metaphysically crucial or changed by predicting in advance. Metaphysically, all there is the relationship between various claims of the data and the evidential relationships between them. And what came first or what happened on Tuesday or Monday doesn't change that. So how does that sort of view that I have of the nature of science tie in with tying your hands behind your back and making sure you don't have analytic flexibility? Well, the way I think about it is there's this nice term introduced, Stiegen et al. In 2016 called the multiverse, although the concept was around before them. I refer to it in a 26 paper, but not by that name. And Karp had done an fMRI analysis with 30,000 different P-maps in 2012. The idea here is when you look at how you analyze even very simple data, there's a number of options you have available to you, which all seem equally good and are not terribly controversial. For example, how do you code some data? I mean, how do you in the Stieg et al. Paper, an example was, how do you decide that someone is, say, in a long-term relationship or not? There was one option, like I've forgotten what it was, I'm currently dating someone. Does that count as long-term relationship or not? A little bit ambiguous. So you can code it one way or the other. Number of different ways of coding that. What phase of the menstrual cycle are you in? A fertile phase? Well, is that day 9 to 15, or it could be 8, 17? You know, there's not a fact of the matter of that. There's a number of equally good ways that you can code this. But when you multiply all the different ways, you could code the variables in a number of different ways. You could exclude participants or deal with outliers. Very soon you end up with probably hundreds of different analyses, and in their paper is over 100, all of which are sort of non-controversial, in the sense equally plausible ways of analysing the data. And all those different ways of analysing the data are your multiverse. So let's say all these different ways, hundreds of different ways of analysing your data, you divide it up into those that were not evidential one way or the other. They had good evidence for H1 or good evidence for H0. Let's say, as in this case, most of the time the analyses will give you good evidence for H0. Well, if you have the data in front of you, you haven't tied down analytic flexibility, you can make little decisions in the light of the data that steer you to the part of the multiverse that fit what you want, and so you end up picking, say, good evidence for H1 if that's what you wanted. Whereas when you tie yourself down, you end up in a random location in the multiverse. And choosing the location of the multiverse in advance, in other words, putting yourself in a random location on it, probably yields the most common conclusion. So therefore, the objective evidential relationship between the data and the hypotheses are respected, probably. So I see tying down analytic flexibility as a shortcut to not calculating your multiverse. Okay? You're getting the most likely conclusion, probably, without having to calculate your multiverse in advance. So, you have to calculate power. And incidentally, that way of looking at registered reports, so there's nothing metaphysically changed by predicting in advance or not, it's just a hack to getting at the objective evidential relationships, also tells you if you didn't pre-register or register in advance, you could still, for example, calculate a multiverse afterwards. Well, I don't think that's a practical solution. Calculate a multiverse for every test you did would be horrendous. Okay, so now to turn back to power. So in your submission to Cortex or somewhere else, you need to calculate power. Where do you get your power estimate? Well, what you want is sensitivity to pick up effects of interest. Well, if you want to have sensitivity to pick up any effect of interest, you need to calculate your power with respect to the minimally theoretically interesting effect size that's just plausible. Now, what you standardly see in papers that do calculate power, whether registered reports or not, is they say something like, Cohen said an effect size of 0.5 is, you know, medium or standard or something. So I'll do it with respect to that. But that doesn't mean that you've calculated power with respect to a minimally interesting effect size. So that's not good enough. I mean, it was never good enough, and it's not good enough in registered reports. Furthermore, I would say standardized effect size is a measure of, well, it's a measure of signal relative to noise. And what you have to bear in mind when you do it, that this, as a measure of signal relative to noise, whenever you change the noise by having more trials in your experiment, more items, other factors in the analyses, Cohen's d will change. The population Cohen's d will change. So you can't just pluck some number out of the air, and you can't even just pluck a number from some past study that was similar. What you sometimes see people do is to pluck a Cohen's d from, say, reaction time and say, well, now we're doing percentage correct. But, you know, it's the same sort of thing, same sort of field, same sort of effect. So that's, I mean, after all, wasn't that why standardized effect sizes were were invented so that we could get rid of our units and not think about what units we're measuring in. But that's not actually doing the job. That's just a huge fudge. Because why should the level of signal to noise be the same for completely different measures like reaction time and percent correct? You might say, well, the past studies have used an n of a certain amount, and indeed this has been recommended procedure for looking at minimal interesting effect sizes. If a level of n in a field is sort of typical or standard, then that's implicitly presuming a certain effect size that's of interest, namely the effect size of that number of subjects and items could pick up on. But that's not satisfactory and wouldn't be accepted at Cortex, because how was that decided? It only pushes the question back, and we need to know how it was decided. A committee has decided that a change of 3 units is a minimal interesting effect size. That's a little bit better, but I don't particularly like that, because why did the committee come to their decision? It's just a black box. What we need is reasons we can criticize and therefore improve upon if necessary. And if the committee could decide on it for good reasons, well, so can you. So what are the reasons you could have? Well, one thing we sometimes ask people to think about is if there's a past meta-analysis or past study, look at the lower limit of the 95% confidence interval. Because that, you could say, is at least some reason for saying that's a just plausible minimal effect size. If that's still theoretically interesting, then it's a minimal, the minimal theoretical interesting effect size that's just plausible. That doesn't necessarily work, though, because the low limit of the 95% confidence interval might be too low to be interesting. But it's just something that might give you some objective guidance. When it comes to applied work, like clinical relevance, you can get good reasons for having a minimally interesting or clinically relevant effect size, because the reason you're doing something applied or clinical is to help some people. And if those people says, yes, this is just meaningful to me, this amount of change, well, because they're the end product that you're interested in, that claim by them is a good reason for saying that this is a minimally interesting effect size. And this has been done in a number of cases. So, for example, Barton et al. Said that a 20% change in BDI, back depression inventory, is a minimal effect size of clinical relevance. Now, you could use that. You might not be using the BDI, but if you're using some other DV, if that was ever measured in the same study as BDI, you could look at the regression of the one against the other and say, well, the change in BDI 20% corresponds to a change of this amount on this amount of learning or prejudice or bias or whatever on my paradigm. And so you can sort of do a conversion between the different units. Or let's say, for example, people are being interviewed about their CV, and you want to tell whether they're lying about their achievements or not. And there might be some standard method that is really pretty bad at telling whether people are lying or telling the truth. But you could ask some end users, maybe companies who want to tell if people are lying or not, how many observations would they just have to shift from one box to the other to make it just interesting to employ this new interview procedure that you're using. I give these examples because these examples I've just had to consider in the last few weeks. Now, when the point of the study is an end user, the end user can decide how much is minimally enough. But for purely theoretical research, minimally interesting effect sizes can be pretty hard to pin down. But you need to pin them down not just for power, but also for equivalence testing, which is also a way you can use in Cortex for registered reports. But you'd need to specify your minimal interesting effect size for a reason. So this is just a little graph on equivalence testing. I'll skip over that. So something else you can do to establish sensitivity is Bayes factors. Now with Bayes factors, what you need to do is specify, because a Bayes factor is one model, say your model of H1, versus another model, your model of H0, say no effect, and it gives you the relative evidence for one of those, for the one model versus the other. So for that to be of any use to you, you have to specify what the model is and why that model of H1 relates to your theory. So you can't just say, I'm going to use JASP and use the default base factors, because there's no reason why a default model would apply to your theory. There are no default theories, right? So you have to specify your model of H1 and why you're using the scale factor that you're using. Now, why would you use a particular scale factor? Well, the scale factor for a base factor, some ways of sort of simplifying how to think about that, and in the end all you have to say is, what's the expected effect size I would get? And then that can be the scale factor. And that's, I find, an easier job than specifying the minimal interesting effect size. For power and equivalence testing, you have to specify logically the minimal interesting effect size. For base factors, just specifying the effect I think I'm going to get very roughly, you see. So in the end, for practical reasons, I find base factors more useful. But it's up to you which way you want to go. That was just some examples. Now, one thing I just want to say about this on power before I wrap up, because this is something that people often get wrong, so I want you to think about. People have some hypothesis that they phrase, and they might test with, a 2x4 ANOVA, and then they give the power to detect an effect being there. But what effect? So in this example, they're seeing how bias will change over blocks, and it will change differently for depressed, for non-depressed participants, for example. But then what they might report is the power to detect bias being above 0. So the power wasn't given for the test of the key hypothesis, it was given for something else. And that's extremely common. It's almost universal in the submissions that we get that the power isn't given for the very tests that are needed to test the theory that's being tested. When a bit closer is to say, well, here's the hypothesis here, so we're going to work out the power for the two-way interaction with 3 degrees of freedom. But the hypothesis given here is a 1 degree of freedom hypothesis. 1 degree of freedom means an effect increases or decreases. If you can say something increases or decreases, that's 1 df. So in order to test that theory, you need a 1 degree of freedom test of it. You need, say, in this case, a linear contrast. The advantage of specifying that way is you'll get the same amount of power with lower participants. It's in your interest to do this. Most of the time, probably, you'll find, if you find that when you specify your hypothesis, you're saying something is increasing while something else decreases, or something's increasing, that's a 1 degree of freedom test. That's easy to calculate the power for, or to calculate the Bayes factor for. People sometimes find it really difficult to calculate power for some repeated measures test with 3x4 or whatever. Well, if you're interested in 1 degree of freedom, that's just a t-test in the end. Okay? So it's easy to calculate your power. So now all these things have to line up in your submission as well. So when you specify your substantial theory, make sure the predictions actually follow from that theory. Check what sort of predictions they are after 1 degree of freedom. Make sure your tests line up with those predictions. So a good way of doing this is to number your predictions that follow from the theory, and then number your tests that test each of those predictions, and make sure they match up. And what you need is high power or high sensitivity, guaranteed Bayes factors of a certain amount for each of those key predictions that test the theory, and for any outcome neutral tests as well. So these things all have to line up. So this is what we would like in our science, and I hope you see how in registered reports, while it's not the only method of sort of trying to ensure this happens, there's no reason why you have to use a registered report to do this. Because of our capacities for self-delusion, we can believe we had that when actually we have this if we look at the data afterwards. So that's what registered reports is trying to solve. I should probably wrap up here. Is my time just about it?
When are we supposed to go to? Half past? Yeah, so you've got...
But some time for questions.
Yeah, exactly.
Yeah, yeah.
Maybe in the next 2 minutes?
Yeah, I think this is actually a good place to stop before going to something else. Because then, so to summarise what I've done, what I hope I've done is shown you sort of a way of looking at science to say how can it go wrong, and then how registered reports addresses those problems. So therefore, what you'd have to have in your register report submissions in order to make sure those problems are addressed. The reason why I've gone through those problems are those are the problems that are commonly missing in the manuscripts that fall on our desk on the first submission. So you tidy them up first. There'll be less toing and froing with the editors before you get through to the next stage. And remember, if you do get through to the next stage, 90% chance, at least at Cortex, that you then get a paper accepted. All right, thank you.